Hi there. This is going to be a quick tutorial on how you can profile your ESP32 application using mabutrace to get a trace view similar to this one. This is a trace of example application, and it lets me see things like the different tasks that I'm running. I can see how long different methods take. Like, for example, my main application loop, I see taking about 10 milliseconds here each. I see the worker tasks that I'm running. I see interrupts, which here, for example, fire every 10 milliseconds and take about 1.5 milliseconds of processing time each time. And here on the bottom row, I see the occupation of the CPU cores. Like CPU core 0 is idle for most of the time, sometimes working on worker task 0, while CPU 1 in this case also idle for most of the time, sometimes working on worker task 1. Now this is called profiling your application. And there are different ways you can profile application. Main frameworks to do that on ESP32 that are promoted is usually Percipio Tracealyzer or Seger System View. Here I'm showing you an alternative which is free and open source and very easy to use. You don't need an additional application. You can get started very quickly. And I will now first start with a quick TLDR to show you the process, and then later go step by step into the details. So what you want to do after you installed the mabutrace library, all you need to do is include the mabutrace header. Then what you need to do in the setup of your application, so that would be like in Arduino, this would be the setup routine, or here in ESP-IDF, it is app main. You'll call mabutrace init, and mabutrace start server, and that initializes the tracer. And then you need to instrument your code by inserting these trace macros. For example, here I want to trace the main application loop, adding a trace here. I want to see how long this XQ receive takes, so I add a trace scope here. And I do that for the entire code that I want to later see in the visual overview. And when I run that, it will give me a server that runs from the ESP. The server from the ESP gives me a capture trace button, which I can click. This will download the trace. Takes a moment. I can save that and I can visualize it. So I get this view. So these are the steps. This was very quick. I now go into the details step by step. And we'll start with how to install the library. So depending on whether you work on ESP-IDF or Arduino, you do that differently. In Arduino, you just go to Tools, Manage Libraries. Then you search for mabutrace, and then you can install it here, and this will make it available for your application. In ESP-IDF, what you want to do is you go to your IDF_component YML file, and under dependencies, you add a dependency on mabuware mabutrace. And that will automatically download the repository and make it available in your app. If you have a platform I/O application, then it depends on whether it's a platform I/O application that uses the Arduino framework, in which case you want to add this libdeps mabuware mabutrace dependency, which will automatically download the library and make it available. And if it's ESP-IDF, So if it's a platform IO project with framework ESP-IDF, then what you need to do is similar to a regular ESP-IDF project, you need to have this IDF underscore component YML file in your source directory, and there you add a dependency on mabutrace. Other than that, it's pretty much the same whether you work with the Arduino framework or the ESP-IDF framework. You can use the library the same way. There's just one important difference. You saw here this bottom line where you see what each CPU core is occupied with at what time. You don't get this bottom line here if you have an Arduino project, because so this bottom trace here of the task switches is traced automatically, but this requires some compile time changes to the core. And since in Arduino we use a precompiled core, this output down here is not possible if you have the Arduino platform. But the top one here, where you have custom traces of your different tasks, of the functions, this you can get both in ESP-IDF and in Arduino. So after you installed the library, I will explain you the next steps now in the ESP-IDF project, but it's really the same in Arduino. We'll have to do the same steps. So next thing what you need to do is, as I said before, you include mabutrace.h, and then in the setup, so this will be in Arduino, this will be the setup method, in ESP-IDF step main method, where you set up all your other things like your sensors and so on. You want to call mabutrace init. This allocates the tracing buffer, which is by default 64 kilobyte of RAM. And you start the server, which serves this front-end page that you saw before to download the trace. After that, the tracing is already running. So one important thing to note is that here on this page that is served by the ESP, where you can click capture trace, clicking that button does not start the trace, it actually ends it, because mabutrace is tracing these timestamps into a ring buffer all the time. And the moment you click on capture trace, it stops the trace and starts converting it to a JSON and downloading it. Okay, so back to the code. After initializing, what we want to do, so here I already have commented out all these trace macros so that we can go step by step. I will compile now the application just after having initialized it and started the server and not doing anything else. If I build the project now, okay, I can flash. So that application has been flashed onto, it's an ESP32S3, which I'm testing on right now, with only having the library initialized and the server started. And if I now look at the monitor output, it will give you this here, mabutrace server started on this IP. And then if I go to web browser, open this URL, this will give me this capture website, which is served from the ESP, where if I click capture again, this will stop the trace. So the moment I click, this marks the end of the trace, and it's now converting the binary ring buffer to a JSON file, also all on the ESP, and you can now download it. So there are actually two ways you can view the trace that you just captured. The first one only works in Chrome browser. So if you're in Chrome browser, what you can do is you can click Save Trace, which downloads the file. And then you want to open a new tab and go to Chrome. tracing. And this brings you to this built-in trace viewer. This is part of the Chrome browser, the front end to view such traces. The first time when you open this, the first time it will show you that you need to enable the developer tools. For that, you need to go to Chrome // Chrome URLs. And here I have it already enabled. So if I disable this, if I go back to this Chrome tracing URL, this is what you will see when you try it the first time. So this is disabled. So you need to go to Chrome URLs and enable these internal debugging pages. And after that, if you go to Chrome tracing, you'll get this front end, and now then you can load the file you just downloaded from the ESP32, and this will give you this view. So it looks like I already have some trace up here, means I forgot to comment something out. If I go back to my yeah, so I forgot to comment out this one. That's why I now see this trace here. But what you would, after initializing the mabutrace library and starting the server, out of the box, what you get on ESP-IDF is the bottom line here, the CPU task scheduling, where you see what the scheduler assigns to different CPU cores. So right now I see actually this CPU 1 is not doing anything. The scheduler is assigning all the tasks to CPU 0. It's also idle for some time, so the idle task gets traced out. The other tasks get traced out, so worker task is one that I set up in my example and start. There, that's the main task, which is this one here. Main task is not taking a lot of CPU time for most of the time. We would also, if you search, we can probably find like the Wi-Fi task, which is sometimes executed. Let's see here, maybe TI. I don't know what this task is, but these are different tasks that are run by the ESP-IDF framework, also get traced here. So you don't need to do anything to get this bottom view here in ESP IDF projects. It just shows you all the task switches and when the core is idle, executing the idle task, or when it's executing some other task. So that's one way you can view this trace. And again, this works only in the Chrome browser. If you're not in the Chrome browser, if you use a different browser, then after having clicked Capture Trace, you can click here, Open Trace in Perfetto. And this requires internet connection. So the previous one would work also in offline mode. This other method that works with all browsers, this requires internet connection. But this will open the trace here in this bit newer front end. It will ask open the trace, you click yes. And then it gives you the same thing. You need to open the traces here. And the navigation is a little bit different. So you need to use the ASDW keys to zoom in, zoom out. But it's basically the same thing. It shows it in a different order here. Now it shows the CPU affinity at the top and the tasks on the bottom. It's the same thing. You can use the keys to scroll around, zoom in, zoom out. Yeah, so these are the two ways that you can look at the trace. Now I will go back and show you how you actually instrument the code. So let me comment out that again. So as said, if you just include mabutrace and initialize it, then here what you get out by default is on ESP-IDF this CPU task switch timeline. And other than that, you don't get any information. In order to get the timing of the different functions that you want to see, you need to insert tracing macros. And the different tracing macros you can see if you go to the mabutrace header. Here it's documented. You can see these are the trace macros that you want to insert into your code in order to trace it out in the trace view. And they do different things. We start with the most simple one, which is TRC and trace scope. So TRC is basically just a shortcut for trace scope. When you use trace scope, you want to give it at least the first argument, which is a string, the name that you will later see here. For example, this app main, or here this find longest palindrome string. This would be the first argument. If you just use the TRC macro, it doesn't take an argument. It actually expands to trace scope with the name of the function it's called in as the string. So if we go back to over here, yeah. So we start, for example, here with, I'm back in the main app function that after is set up goes into an infinite loop, which is the main application loop. In Arduino, this would be the loop function, for example. And I want to create now a trace for each iteration of this main loop. So I enter a TRC macro here at the top of this scope. And this TRC macro would be equivalent to saying trace scope app main, because it is called from the app main function. So TRC automatically takes the name of the function and calls the trace scope with app main. This statement here, this will be responsible for this block here, the app main trace that I see in this view, taking 10 milliseconds each iteration. But I want to get some more info what happens during this trace scope. So for example, it's here, it's waiting for a message from this queue, Q2, and I want to see how long just waiting for this message takes. So I can create a scope around this function call. A scope is everything between curly brackets, and any trace scope statement will, so you need to insert the trace scope macros at the top as the first statement inside the scope, and it will automatically take a timestamp when the program flow enters the scope, and it will take another timestamp when it exits the scope. So by creating a scope around this function call here, and then inserting this trace scope macro with the string xq receive q2, this will give me later in the trace this bottom line here. And if I zoom in here, so under this app main, let's go back to the code. We're still here in the main application loop that's tracing out each loop here, and it's tracing out the subsection, waiting for this queue. And then down here, I also want to see how long it takes to for this print statement down here. So I also add another trace scope here, scope printf. Printf here is just the name that I want to see later in the visualization. And what that gives me here is, again, so this is the main application loop. And then if I scroll in here, I see most of the main application loop time is spent in waiting for the item in the queue. And then I can zoom in here. The print actually takes very, very little time. So that's what I can see here now. There is also here a read temperature because in this code, I have another code block here where I'm reading the temperature of the ESP using the internal temperature sensor, and then there is this both a scope that shows me how long it takes this temperature reading, and then I also have a statement trace counter, but I will go into the trace counter statement later. But anyway, so trace scope read temperature here corresponds to this time duration, only takes 0.03 milliseconds, so it's very quick. I see most of the time is spent in waiting on this queue. Then this example application also spins up two worker tasks. Let's see here. So depending on the number of cores, it creates as many instances of worker task method, which I have defined up here. So I'm currently testing on an ESP32S3, which has 2 cores, so it will spin up 2 tasks, 2 instances of task, worker task, each with a stack of 248 bytes. And it's xtask create. I'm not using xtask create pinned to core. So by creating a task like this, xtask create, I'm leaving it up to the FreeRTOS scheduler to decide on which cores it wants to run these tasks. So we get 2 instances of worker task, and what worker task is doing, it's also just waiting for a message from a queue, and then it runs a method. It's called find longest palindrome, and then it adds the result to another queue. Maybe I should quickly explain what this example application, which I'm profiling here, is actually doing. It's not doing very meaningful work. It's just to give an example of how you can use mabutrace to profile it. But what the example application is doing is it's setting up a timer that fires every 10 milliseconds and calls on timer. And this will be called in an interrupt. So every 10 milliseconds an interrupt on timer is called. Then it allocates a message. Message is just struct with a character buffer of 256 characters. It also has an integer link here. I explain later what this is used for, but it's mainly just a message. A string buffer, 256 characters. And it calls random fill on this buffer. And random fill is here. It's just a method that fills the buffer with random bytes and then maps these bytes to the range of ASCII letters from A to Z. So the output after calling random fill will be an array of 256 random characters from A to Z. So that's what's happening in this interrupt routine, and then it is sent this message to the Q1, where it will be picked up by the 2 worker tasks. So this happens in the interrupt. Then the worker task here will periodically wait for these messages that have been put into Q1 by the interrupt, waits for them, and as soon as one is available, it runs find longest palindrome on this buffer. And find longest palindrome is just a method here that searches for the longest substring in this string of random characters that is a palindrome. Palindrome being a string that reads the same from the front to the back. So here it's already running on the bottom. You can see the output here. All these strings are palindromes. And this method basically just searches for the longest such substring, this is a palindrome, and then writes it back into buffer. So the result will also be output in the input buffer. So what the worker task is doing, It's getting the message from Q1, calls find longest palindrome, and then adds it back to Q2, the result. Pushes it to Q2. And then finally, we have in app main, the main application loop. Here in Arduino, this would be the loop method. And here the main application loop is also mainly waiting for the messages to arrive in Q2, taking them from there, and then only if the length is longer than 7 characters, it will print out here, palindrome generated, and will print out the output here. Yeah. So in order to get this complete view here, I want to insert trace macros also in this worker task, for example. So here I could use instead of trace scope, I could just like add this, and then it would say worker task, but I want to use a different string in the visualization, so I use trace scope instead, which will trace as worker task loop. Then I want to see how long it needs to wait on the messages here in the queue, so I create a scope around this method call and add a trace scope in here. And finally down here, I also want to see how long, whether it's like, it could be when it pushes the messages to the queues. If the queue is full at this time, it will have to wait. So I want to see in my visualization if it actually has to wait here on sending the message to this queue. Further, like here, the find longest palindrome, I also want to see in my trace. So I added TRC statement just at the beginning. This will, again, adding that, will take a timestamp at the beginning of the scope and then another timestamp at the end of the scope for later visualization. Random fill here, I also added TRC, and that's like a good start. So you want to start by just adding a TRC macro call at the beginning of your main methods. If you just do that, this will already give you a good idea of what your application is doing. So here I add some sub traces. I want to see how long ESP fill random takes. So I add this trace scope. And then after filling with random bytes, I'm remapping them to the A to C characters, and I want to see how long that takes. So I add another trace scope, calling it map range. Yeah, we don't need to trace. So, oh, and here, this is the timer interrupt. We can also use the TRC macro in interrupt. That's no problem. The rest I leave. So now I just added these TRC and trace scope macros in my code, and I will recompile that and look at the result. Okay, so I flash. Monitor device. Okay, so now it's running again. I can go back here to the trace capture webpage says served by the ESP. And again, so the moment I click capture trace marks the end of the traced segment. Saving the trace, going back to Chrome tracing, loading that file that I just downloaded. And the length of the entire trace, so here you see it captured about 3 seconds. The length depends on how many tracing macros you insert, because mabutrace is continuously saving these timestamps into a ring buffer, and that ring buffer by default is 64 kilobytes. So the more tracing statements you take, the shorter the entire duration that it captures will become. So keep that in mind when you enter insert tracing macros. So, but that's now what I get. So again, I see my main application loop. That's on the main task. I see the two worker tasks that are spinned up here. That's the main worker task loop. Each one on each core taking about 20 milliseconds. Waiting for most of the time for the messages on Q1, and then running find longest palindrome. And I see here the interrupt routine, which is executed on CPU 0. I see that it takes about 1.4, 1.5 milliseconds each time. And if you remember, so we traced here the random fill method, and we also traced these two subscopes here, the fill random method call, as well as the mapping to the A to Z range. If you look here, now we see that. So we see the whole on-timer method takes about 1.5 milliseconds and completely occupied by this random fill method, and this random fill method call itself spends most of the time in the ESP fill random method, and then here very short time, only 0.04 milliseconds in the map range part. So and this gives you an idea of where your application spends the most time. It gives you an idea of, if you, for example, if you want to do performance optimization, it gives you an idea of where you can like have the most return on investment if you optimize the performance. But here, for example, now everything looks quite fine. So one CPU core is completely idle. The tasks scheduler of FreeRTOS doesn't seem to need to make use of CPU1, and it packs both the worker task 1, worker task 0, and worker task 1 both onto the same CPU core. But since we created these tasks using xtask create, it's really up to the scheduler on which core it wants to run it. So now these are the most basic trace macros that you can insert. There are also a few other ones which trace slightly different things. And if you go back to maybe trace header, there are like these other trace macros that you can the other things that you can trace. That's mainly flows, so trace flow out and trace flow in, and these statements you want to use, these macros you want to use, if you have some program flow across task boundaries. So if you have some asynchronous behavior between multiple tasks and you want to trace that, you can use these trace flow macros. Then if you don't want to trace a duration but a specific instant moment, then you can use the trace instant macro. And then finally, you can also use trace counter to trace a value, an integer value in particular. It's assigned a 24-bit integer that you can trace. And I will show you now how I use these in the example application. Let's go back. So let's go back to the main loop. So here, if the ESP I'm using has a temperature sensor, I do use this temperature sensor get Celsius to get the internal temperature of the SoC. And I'm already here tracing this read temperature. We saw this here in the trace. No, that's a print. Here, that's a read temperature. It takes a very little amount of time. If I enter here this trace counter statement, so I only added this here, trace counter temperature, and I round the temperature to an integer, trace it here, and let's just compile that and nothing else. Okay, flash the device. Okay. So now it's running with this trace counter macro inserted into the code. And what I will do now, before I capture trace, I will blow onto the ESP32, and hopefully we will see that the temperature is going down. So right before I click capture trace, I blow onto the ESP32. Clicking capture trace. Save that file, open it. So now we got a new, here on the top, the temperature bar that traces this, like it's about 41 degrees Celsius that we can see. It's going only slightly down. So you see it started at like 41 degrees. And then when I blew onto the SOC, I don't know whether you see that in the video. So here on the bottom, if I click on here, you can see the value that is traced with this counter, and started around 41 degrees Celsius. And then at the end here, right before I clicked, it was down to 39. So not a lot of variation. But anyway, so this trace counter statement allows you to trace an integer value together with the rest of your trace. And you can use that, for example, it's useful to trace like how much free memory you have on your heap, or any other integer that could be relevant for your trace. Then another one that we can use was the trace instant. And so if you go back here again, I start, the application starts by running an on-timer event in an interrupt and filling that interrupt with random characters. And then it pushes this random string onto the Q1. And because this runs in an interrupt, we have to use XQ send from ISR, not instead of XQ send, which would be the normal one to use from a regular task. But XQ send from ISR has no way of blocking, because it's an interrupt routine. It's not allowed to block. So what will happen is that if the queue should be full at that moment, instead of waiting until it's free, it only can just fail, not push it. And here instead the XQ send from ISR will just return an error queue full if the queue is full, and not push the message onto the queue. And we want to trace this now in the view as a trace instant. So I added this here. If the queue should be full, trace this instant. Now, because I ran this already previously, I know that actually at the moment, the way the sketch is set up, it's never full. So the moment because as you can see here, we run these two tasks that process the messages generated in the interrupt, and they're fast enough to keep up with this 10 millisecond interrupt. So actually, whenever the interrupt is finished, the queue always has space. But if we increase the length of this message buffer, so it's 256 characters at the moment, so let's increase that to Let's try 350. So now I increased the message size here just to give it a little bit more work to do. This, especially this find longest palindrome method is O(n) square, so it will increase in duration quite quickly. And so that's what we did. We changed the length of the messages that are generated, and we added this trace instant here whenever Q1 is full. And I'm going to compile this now. Slash. Okay, now if I go back and take another trace, capture trace, opening this new trace. So here we see now these red lines, and each of these red lines is one of these trace instant calls. So, and because we only issue those if the queue is full, that tells us now that, oh, okay, it looks like every 1, 2, 3, 4, 5, 6 interrupts. Actually, the queue is full at this moment, and the interrupt cannot push the message onto the queue. We also see that the find longest palindrome method has increased in duration, so it takes about 12 milliseconds now to process, which is longer than the 10 millisecond interval of the timer that fires. So we get this full queues every six interrupts, but actually this should not happen because we have two worker tasks. So, and the find palindrome method now takes about 12 milliseconds. Here 13, which is longer than the interrupt interval, but we have two worker tasks. So actually, they should be able to keep up. But as you can see here, and I cannot explain you why, but it seems like the scheduler of FreeRTOS is a little bit stupid. And even though like CPU 0 is completely idle, it's not putting the worker tasks onto the other core. And this is quite flaky. So I've run this example before, and I saw sometimes the scheduler will actually put one task onto one core and the other task onto the other core, and then it's able to keep up. But right now, it seems to put both worker tasks onto the same core, and because the find longest palindrome method takes longer than 10 milliseconds, it's not able to keep up with the interrupt. So to fix this, for example, so here I could see now, okay, this is a problem. What can I do to fix it? In this case, I could say I explicitly create the worker tasks pinned to the different cores so that we actually use both, get both cores utilized properly, instead of relying on the scheduler to do a smart thing, which it apparently is not doing here. So let's change this X task create here and replace that with X task create pinned to core, if I remember correctly. And then we need to add one argument, which is the core idea. So now it creates the two tasks, with the first one pinned to core 0, meaning it can only execute on core 0, and the second instance can only execute on core 1. And if you now, without changing anything else, yeah, we get actually what. So that's also interesting. If you can see here, the output down here, we get on CPU 0 currently the task watchdog is getting triggered, and that's obvious if you look at this trace here, because CPU 0 is busy all the time. Like it's never actually getting into the idle task. And this will cause the idle task watchdog to get triggered if there is never any lowest priority time available for the idle task on the core. And that's why we get these here watchdog got triggered error messages, because core 0 is never idle and the idle task on core 0 never runs. But now we change this xtask create with xtask create pin to core, and what we would expect afterwards is to see that instead of having CPU 0 execute both worker tasks in series, have these two tasks be distributed onto the two cores and execute in parallel. So let's try it again. Build project. Flash device. Starting it up. Okay, it's running. Then capture trace. Open the new trace. So now, as you see, the red lines that we saw before, there are no red lines anymore. And now we actually see that worker task 0 is only executed on CPU 0. Worker task 1 is only executed on CPU 1. And even though these find longest palindrome still take longer than 10 milliseconds, because they can be executed in parallel, as you can see here, like in this time frame, for example, two instances of this find longest palindrome method are running, one on in task 0 executed on CPU 0, one on worker task 1 executed on worker task 1. And because of this parallelism, now even though the actual duration per core is longer than 10 milliseconds, it can keep up with this timer interrupted fires every 10 milliseconds, and none of the messages generated here hit a full queue. Yeah. Okay. Then finally, what I want to show you is how to use these flow traces. And the flow traces you want to use when you have some asynchronous behavior, which we have in this application. So we have the interrupts. Let's go to the interrupt here. We have the interrupts which generate a message and put this onto the queue. And then we have some worker tasks which pick up these messages that have been put onto the queues. And this is not happening in series. This happens in an asynchronous way. And if you want to get an idea of, for example, how long it takes between the interrupt pushing that message onto the queue and the worker task actually getting the item and processing it, we can use these flow traces. And that's a bit more involved than just adding a single statement. What we need to do here is we need an integer link ID, because the trace needs to later be able to associate the start of an asynchronous flow with the end of an asynchronous flow, and for that you use a link ID. And we start a flow with this trace flow out, and we pass a pointer to this link index as an argument. And after calling this trace flow out macro, this link index will contain a pointer that we need to pass along the message to later use in the trace flow in macro. So I show you how that works. I use here before I send the message onto the queue, I call the trace flow out macro with this link index. Then I add the link index to this message object that I defined here, if you remember. So this message object has the character buffer, plus it has this link argument, which you need exactly for this. So we define the link index, add it to the message, push it onto the queue, so Q1, and then in the worker task, here where we get the message from the Q1, after getting the message, we add a trace flow in statement with the link argument, so the index argument that we passed on along with the message. So again, conceptually, in the interrupt here, we use the trace flow out with the link index, and then here where we consume this item on the queue on the worker task, we add a trace flow in with this link index. It's just a 16-bit index. So if we compile this, flash device. Okay, so if we take a capture now, so what we get now here, if you use a flow macros and you don't see anything, then you may need to click here on top on flow events and make sure that this here is enabled. And now we see that here on the interrupt, after the message has been created, it's put on the queue, and we get like this flow arrow to where the worker task here, worker task 0, actually picks up the message and then processes it in here. So this is currently happening very quickly because we have 2 worker tasks, each spending about between, looks like 10 and 12 milliseconds of processing, and we have the interrupt that fires every 10 milliseconds, so it's very easy for them to keep up. So this arrow here, it's very short, so very immediately after the interrupt puts the message onto the queue, there is already one of the tasks waiting to process it. But let's see what happens if we further increase the length of these messages. Let's try 400. And see how that looks. So, capture trace. And again, you could also see the trace in Perfetto if you prefer that, but personally I like Chrome tracing better, which is the older interface for this, but I like the navigation better. So now we increase the message size, and we can see that again in the interrupt, we hit the full queue sometimes. And we also see that the processing now of messages generated into interrupt doesn't happen immediately. There's quite a delay, and that's because like both worker tasks are busy at the moment this item is pushed to the queue, so there is no free worker task, and it takes until one of the tasks gets free again before it can be processed. And that we see very nicely with these flow traces. Then we also see some other interesting things. For example, that on worker task 0, the find longest palindrome method consistently seems to take longer than on worker task 1. And that's because we have this interrupt that is executing on CPU 0. And interrupt handlers always just hijack the stack frame of the task that is currently running on the CPU. So they will execute inside of this task that is currently running. So inside of this find longest palindrome method, if you want. So that's why here this one takes longer. And what we also see, which is quite weird, is that XQ sends Q2. So after find longest palindrome found the palindrome and pushes it onto Q2, this blocks, meaning that the queue is full at this moment. The queue has a size of 2 items. But it's quite weird that it's full, because at the same time we see that the main task, which is consuming these items on Q2, it is blocked waiting on Q2. So this is in XQ receive on Q2. And this task blocking on Q2 means it has 2 items at the moment, so it cannot push any more items. But then we should actually see the main app taking these items and processing it. So it's quite weird that it's still waiting here. And the problem here is that the main task isn't given any time to process by the scheduler. So we see at the moment that task 2 is blocked here. Down here we see that CPU 1 is actually issuing a task switch, and it falls back onto the idle task. And that's weird. So we would actually want to see, at least here, where the task gets blocked and a task switch can happen, we would hope for it to switch to the main task so that it can process items here. We actually would want it to process already sooner than that, but no later than this. The idle task has the lowest priority 0, and main task by default has priority 1. So it's very weird that here we don't see the main task running. And there seem to be 2 issues that cause this. One is actually that by default the main task is set to only execute on CPU 0. So if you go to the SDK configuration, search for main, here main task core affinity is set to CPU 0. So the main task is only allowed to run on CPU 0. We can change that to no affinity. And then we should hope that it could also run on CPU 1. Let's see, is it safe? Yeah, let's try this. Okay, so now we set the main task to no affinity, so it should be able to run on either CPU 0 or CPU 1. But we actually see, yeah, here it runs on CPU 1. That's good. But now it looks like, yeah, it looks like the scheduler, for some reason, only schedules it to run on CPU 1. We never see it running on CPU 0. And now we get the same problem here on CPU 0, waiting. It has to actually wait until here on CPU 1, so worker task 1 finishes, and on CPU 0 there is some time for the main task processing these items that are waiting on Q2, and only then actually the XQ sent to Q2 on worker task 0 can finish. So now worker task 0 has to wait for worker task 1 to finish so that the main task actually gets some time to run to clear this queue. I can't tell you why the scheduler doesn't decide to run the main task here. So we set it to no affinity now, which should actually allow it to run it also here. But for some reason it decides to only run it on either CPU 0 or CPU 1, but not switch it. So we need to find another solution for this. And one thing could be to insert some vtask delay into find longest palindrome, just to give lower priority tasks some time to run. But something else that we also can do is we can lower the priority of these tasks to the same priority as the main task, which should allow the scheduler to preempt the tasks at any moment and switch to the main task. So here now we change the priority to 1. Now they have the same priority as the main task. And let's try this. Okay. Node. Yeah, and now we see, now we don't have the problem anymore. So now we don't see any wait anymore on the send, which is good, meaning that the main task actually gets time to run. So here it runs at the end. Oh, here. So we see that now on here, find longest palindrome actually gets preempted. So we see that CPU 0 is working on worker task 0, which is running find longest palindrome. Then here in between it switches to main. So it switches to the main task, it does some processing that is due, and then it switches back. So the find longest palindrome method, this task gets preempted to give some time to run for the main loop. And now it can actually keep up with processing the messages that are on Q2. We still get a delay here because now actually find longest palindrome is really saturating both cores, and it takes a while until the task becomes free to process the next item. But we get only a few full queues now in the interrupt. And now we could go into actually performance optimizing these methods to do even more work. But now we see we have very little idle time on the cores. We don't block when sending onto the queues because we give time to the main application loop to process. And debugging such issues or optimizing such issues is really difficult or almost impossible if you don't have a visual aid to see what's actually happening. And that's what is the main benefit of profiling your application. So I hope you found this helpful. Maybe let's do a recap on the different profiling methods. The different trace macros. You use the TRC or the trace scope macro to trace here the duration of scopes. So these are these that give you a duration of some code block. And by the way, there is always an optional color argument that you can use. So here, for example, I pass the color yellow because I want it to always be visualized in yellow when it blocks on the queue. But I can just omit the color argument, and then the visualizer will choose a color at random. So yeah, so that's trace and trace scope, which is probably the most important one. Then you have the trace instant macro, which is used to visualize these lines here when some event happens where you're just interested in not the duration of the event, but just that something happening. And then there is the trace counter, which you can use to track the change of an integer value. Here I use it to trace the internal temperature of the SOC. And finally, the trace flow out and trace flow in statements, which you can use to visualize asynchronous application flow. So this creates these arrows. You start with an trace flow out to mark the start of such an arrow, and then you use a trace flow in together with the integer link that you got when you made the trace flow out macro to visualize the input of this asynchronous application flow. Yeah, so that's actually all the relevant trace macros, and you could see a bit how you can use this to get a better understanding of what is happening inside your app, and also figure out exactly such puzzling things like we had here. Why is it waiting on this queue when it should not? I hope it's helpful for you. If you have any questions about mabutrace or performance optimization or performance analysis in general, feel free to reach out. One more note about mabutrace: it's open source and released under the GPL v3. So if your project is not GPL v3, you should remove the library again before you make a release. But since this is actually just a tool that you need to use during development anyway, that should not be an issue. Okay, so hope that was useful for you. Cheers.